That's a familiar tune. How do instruments like guitar create music? We'll talk about the science of sound and some of the properties of sound waves, but when we talk about sound waves in the context of music, there are all kinds of fascinating properties and rules to talk about. I'm talking about the music that comes from string, wind, and brass instruments. String instruments create sounds when their strings vibrate in the air, and in order to understand how these instruments work, we have to realize that making music is not just an art, it's also a science. Sound, as you recall, is a wave, a longitudinal wave. This means that the medium that the wave travels through oscillates or moves back and forth in the same direction that the wave is moving. But string, wind, and brass instruments will use a special kind of wave, the standing waves. A standing wave is a wave that looks like it isn't moving. Its amplitude may change, but it isn't travel anywhere. Standing waves are the result of two other things waves do, both of which we'll talk about it before: reflection and interference. Reflection is what happens when a wave reaches the end of the path and then moves back along the same road. That's what happens when you send a pulse down a road. It reaches the end and then comes right back. When we send a continuous wave down the road, that's when interference comes into play. The wave reaches the end of the road and it is reflected, but there are more pricks, and as the pricks pass each other, they interfere with another, changing their size. Usually you end up with crests and torque that are different sizes and various distances. But at a certain frequency, the reflected waves interfere in such a way that with a wave that seems to play perfectly still, with only its amplitude changing. That's a standing wave, and it can happen both in string and in the air in pipe. And that's what makes music. Standing waves with different frequencies correspond with different music notes. Now, in order to understand how standing waves operate, you should get to know their antennomy. The points of a standing wave that don't oscillate are called nodes, and the points that are maximum height of the peaks are antinodes. And here are something cool. If you look at a string on a string instrument, you can actually see where the nodes and antinodes are. The standing waves create peaks along the string, and between those peaks there are points that just stay still. So the peaks are antinodes, and the points that don't oscillate are nodes. And if one or both of the string ends are fixed, then the fixed end is node 2 because moving back and forth. Now in a pipe, the standing waves are made of air molecules, but the air where molecules, including those near any open ends of the pipe, form the peaks and therefore the antinodes. And between those peaks, as well as any closed end of the pipe, there are areas where molecules don't move at all. Generally, musicians make their music using the frequency of these standing waves, but the nature of these waves depends a lot on what the end of their string or pipe look like. Remember how a wave traveling a rope gets reflected differently, depending on whether the end of the rope, a fixed end, will invert the wave, turning crests into tops, while a loose end will just reflect it without. The same thing holds true for air in a pipe. A closed end will invert the wave, while an open. So the property of a standing wave will be a little depending on whether it's made with a string with two fixed ends or pipe with two ends open, and a string or a pipe with one end fixed and the other open. A string with two fixed ends, like a piano, is probably a simplest way to understand standing wave, because we know that no matter what the wave made by a fixed string will have at least two nodes, and in its most basic form it would have just one antinode. So the wave is basically a peak that moves from being a crest to a trough Like some kind of this most basically kind of standing waves known as fundamental or the ones. If you simply possible standing wave you can have with the fewest, there are other more complex standing waves. These known as overtones. Overtones build on a fundamental incrementally. Each overtone adds a node and antinode. So each of these antinodes is related to the fundamental wave, and all of the overtones are related to each other. Together, the fundamental wave and the overtones make up what are known as harmonies. The fundamental is the first harmonic, and the overtones are higher number harmonics with each node and antinode pairs that are added. The number of the harmonic goes up to second harmonic, third harmonic, and so on. Now, physicists sometimes express harmonic in terms of wavelength. For example, for a string with two fixed ends, you will notice that the fundamental covers exactly half a wavelength, and full wavelength of the wave would span two waves, a crest and a stroke, but the fundamental span is exactly one peak, which half. So the fundamental of string with two fixed ends, the length of the string is equal to half a wavelength. The second simplest standing wave you can have on a string with two fixed ends has three nodes, one at each end and one in the middle, plus two antinodes in between the nodes. It's called the second harmonic, and the string holds exactly. You can probably guess that the third harmonic looks like it has four nodes and three antinodes, and the string holds 1.5 or 30. You might have started to notice a pattern for a standing wave on a given length of string. The number of wavelengths that fit on the string is equal to the number of the harmonic divided 2. So now we have an equation that relates the wavelength of a standing wave to the number. Once you handle with a wavelength, you can figure out the aspect of the wave that musicians care about most, the frequency. You already established that a wavelength, sometimes its frequency is depend on the medium it's traveling through, which will be the same for each harmonic, because a wave, so standing wave frequency will equally to its for the fundamental with two phase n, and we already know that the wavelength is twice. So the frequency of that fundamental standing wave known as is equal to the velocity divided by, we write it as. Now, what about the frequency of the second harmonic, the standing wave with three nodes and two antinodes? It will be equally to the velocity divided with is twice the fundamental, and the frequency of the third harmonic with its four nodes and three antinodes, which will be equal to 3 times for the fundamental. So we are starting to see another pattern. The frequency of standing wave with two phase n will just be equal to the number of harmonic times the fundamental frequency. In fact, that's one way to define harmonic. The number of harmonic is equal to the number multiplied by the fundamental frequency to get the harmonic frequency. This math is what makes music instrument work. When you press down a key on a piano, you make a hammer track. A string creates stand waves in that string. Every string in the piano is turned so that the fundamental frequency, which depends on the string's mass, length, and tension, correspond. Middle C, for example, is 261 Hz. Guitar is also turned up that the fundamental frequencies of that string, and when you press down on the string in certain, you change the length of an active part of string so that its fundamental frequency corresponds to a different note. So for a standing wave with two phase n, we can relate the wavelength, frequency, and the length of string and the number of the harmonic. And we can do the exact same thing for standing wave with two loose ends and in an open pipe, for example, like a flute. A standing wave in a pipe with two open ends is kind of the opposite. instead of having a note at each end, it has so the fundamental standing wave for a pipe with two open end will have two antinodes and one note in the middle of the wave. Then the second anharmonic will have three antinodes and two notes, but each harmonic will cover the same number of wavelengths. Remember how the fundamental wave for a string will to fixed end cover half of a wavelength. The fundamental wave for a pipe with two open ends will also cover half of the wavelength. That half of just in a different and just like a string with two fixed ends. The second harmonic for a pipe with two open ends also cover a full wavelength. It's just that the case of the pipe and the wave start and end with a pitch. So the equation for wavelength and frequency for a standing wave will be the same as they were for a standing wave with so we've covered guitar and piano and flute, but a pipe with one closed end and one open end works differently. These kind of pipes are used in instruments like pan flute, where you blow across the top. Here, standing wave need a separate set of equations. First, the closed end of a pipe will be a node because the air molecules, and the open end will be an antinode because that way they are which means that the simplest wave you can make with a pipe will stretch from one node to one peak and was only a span of quarter of before with both a string fixed at both ends and an open pipe. The fundamental span half. The fact that a pan flute pipe only covers a quarter of the wavelength change because remember the frequency of each harmonic is equal to the number of harmonics times the fundamental frequency. But for a pipe that close to on one end, you can double the fundamental or quadruple it or multiply it, because it would result in a wave that would need a node on both sides, which isn't possible. So a pipe that closely on one end can have even number. All that of these have explained why musical instruments sound different. When you play a note, you create a fundamental wave plus some of the other harmonics, the overtones. For each instrument, different harmonics will have different amplitude and therefore sound louder. But because of the physics of standing waves, instruments that have one create the even number harmonic at all. That's why a C on the flute sound so different from the C on one side. Today you'll learn about the standing wave and how they are made. We discuss harmony and how to find the frequency of standing wave, two fixed ends, a pipe with two open ends, and a pipe with one closed end. Finally, we explain why a pipe with one closed end can't have any even number. Class physics is produced in association with PBS. You can head over their channel and check out a playlist of the latest shows like first person and the good stuff. This episode of Crash Course was filmed in the Dr. C. Kinney Crash Course with the help of this